with the next speaker. And I'll be moderating this session. Let me introduce Cengiz Onbaşlı, a brief introduction about him. He's a professor at Koç University. He received his bachelor degree from Bilkent University Electrical and Electronics Engineering Department. Then he moved to MIT for his PhD. Then he has a short period of the work over there. Then he joined to the Koç University. He's currently interested with the fabrication of magnetic films and devices, sensors, electronic microprocessors, and telecommunication components. Today, he will talk about the advanced quantum sensing, applied quantum sensing. Sorry, excuse me for that. Let's hear from Professor Onbaşlı. Please.
Thank you very much. Thank you very much, Hocam. Can you all hear me well? Okay, you can see my screen as well. All right, thank you. So my name is Mehmet Cengiz Onbaşlı, and this is also an announcement that we are looking for new PhD students. So with that, I'm going to also advertise our open positions for quantum sensing in the lab. I want to start off by asking you about your backgrounds first, so that I can tune or calibrate my terminology or speed. If you could please raise your hands if you are graduate students. Can you please raise your hands if you are graduate students? Okay, 1, 2. Okay. Any other graduate students? Okay, so we have a few. Okay, you may now lower your hands. So let's hear about the undergrads. How many of you are undergrads? Okay, so we are aiming for more of an undergrad group. Okay, that's best. I think it is better because I want to keep things simple, and I want to actually start off by giving you an idea about what we are looking at. I'm going to share with you the slides after this session, and I'm going to actually send the Google Drive link, so that you can refer to the slides immediately after the presentation. So in fact, I refer to several references as I overview this tutorial lecture for quantum sensing. Thanks to Özgür Hoca's preliminary derivations, we will be able to build on the practical side of the quantum sensing. In fact, the punchline of his presentation about shot noise limit has been a critical point where I will take from. And I'm going to explain to you how quantum sensing can actually go beyond shot noise limits using entanglement and other quantum specific advantages. You may see several figures here. These are about diamond NV centers and optical interferometry, which basically exceeds the Rayleigh limit for sensing and detection. And please read these references after our tutorial session, so that you can get a better sense of the terminology and other applications of quantum sensing. So let me introduce myself a little further. So I'm also affiliated with the Quantum Metrology Institute, Quantum Metrology Lab at TÜBİTAK UME, and we have been developing quantum sensors as well in the lab. So I bring together material science and electrical engineering, and we have been doing materials epitaxy for quantum materials and sensing. And we have been actually recruiting students for graduate studies. So especially those of you who are graduating soon, please contact me so that we can interview. So applied quantum sensing is actually mostly about understanding how we exceed the state of the art of classical sensing. So to do that, to be able to understand that, we need to first establish a good understanding of how classical sensors work. And then we are going to go into how quantum sensors actually build on top of that. So that's why I'm going to first start off with the sensing in the classical manner. And then I'm going to explain how we are going to build on top of it. So as you may think about sensors in our daily use, we can basically retrieve or see some external physical stimuli, for instance, heat or magnetic field or electric field or light. And our sensor somehow converts this change into a voltage or a current as a function of time. And then using our sensor's calibration curve, which is actually its typical characteristic for how it converts temperature to voltage, we actually back calculate the voltage that we read and we back calculate the temperature that we actually want to see. So at the end of the day, we are essentially referring to this one-to-one correspondence between the voltage and temperature in this temperature sensor example, where we get the heat, and then our sensor basically detects the output as a voltage as a function of time, and then we calculate the temperature. This is a classical sensing scheme. There's nothing quantum about it, and let's understand where quantum starts picking up and how its advantages are going to be relevant. So to understand that, we need to define our signal-to-noise ratio and dynamic range, and those are going to be actually highly relevant for our quantum sensing applications as well. So when we talk about signal in a sensor or in any applied quantum sensing, we are referring to actually the sensor readout, which is the output as a current or a voltage, and it has to have a relation to the physical stimulus which we receive from the environment. And it has to carry some information, meaning we are trying to retrieve some distinct feature out of the background. So that's why we need to actually retrieve some specific features like either a spectrum peak or a peak in time or a peak in space, things like those. And then we look into noise. Noise is essentially irrelevant background effects, regardless of whether those background effects can contain information or not. We only want to focus on the information content that we are interested in. That's why when we look into the spectrum of peaks, we are only interested in the peaks that are relevant for our environmental stimulus. That's why when we look into the signal-to-noise ratio, we actually integrate over the integrate the signal power over the total noise, and then obtain a signal-to-noise ratio. So essentially, this leads us to how sharp signals we receive for our magnetometers, gyroscopes, or photodetectors. That's why if you want to do microscopy or any other kind of detection, signal-to-noise ratio is actually going to be highly relevant. And in the dynamic range aspect, we're also referring to the ratio of the largest measurable signal to the smallest measurable signal. In this case, we want to understand the power ratios and their logarithms, or the voltage ratios of maximum and lowest detectable signals, and we want to see how many decades or dBs of differences we can detect. So you can refer to this as the as our microphones, which can detect tens of dBs of sound scale. So that's why we are referring to the dynamic range as the detectable range. In addition, there's also bandwidth. So bandwidth is actually quite relevant for quantum computation and quantum sensing, because this is going to set the qubit quality and also the sensing signal-to-noise ratio. We are essentially referring to the detectable range of frequencies for our sensor operation in the bandwidth. And when we look into our analog to digital conversion, this is essentially discretizing our voltage readout from our sensors, and we are turning it into digital binary values using a component that we call analog to digital converter chip. So ADC chip is actually what we use for our analog to digital conversion. And this is actually relevant for signal subtraction or background subtraction, and that will be highly relevant for especially the applied part. So now let's think about classical sensors based on quantum phenomena, and I'm going to distinguish these types of sensors from the purely quantum features. So when we refer to quantum phenomena, we are actually referring to discretized energy levels, which help us identify the state transitions as a spectrum peak. But in our case, in the classical sensors, we actually have discretized energy levels, but the mechanism of sensing is not necessarily quantum. So that's why there's a wide class of sensors that use classical mechanisms for signal transport or detection, but they make use of quantum phenomena that occur in materials. So one example here is a photodetector from Osram. So I looked it up from a vendor's website, and there's a PIN silicon photodetector. So in this case, what we see here is this is the photodetector's packaging, and we send light onto this chip, and we detect the photocurrent out of the leads of the sensor. So the way it works is we have this energy band diagram where as we are traversing through the doping regions, we observe differences in valence and conduction band energies. And when we send our light into our chip, we actually identify the fact that our electrons that are sitting at the bottom of our valence band get excited to the bottom of the conduction band, and we are essentially separating our excitons, which are quasi-particles that actually help us pick up our photocurrent at the contacts. So you may have noticed that there's a discretization that originates because of the long-range crystalline order. So if our materials were not demonstrating any long-range crystallinity, then we wouldn't observe this kind of a band gap in most cases. And that's why we actually make use of this quantum mechanism to understand and achieve classical sensing. So here, photodetection in its broadest sense is not necessarily a quantum sensing method, but since its optical phase and amplitude are may not necessarily be coherently detected. So the key term here is the coherence. So we want to detect entanglement, or we want to detect superposition states, or we want to detect coherent phases of incoming quantum states to be able to have a truly quantum sensing mechanism. But in most cases, photodetectors are used for classical sensing just by using quantum phenomena. And I'm going to refer to the cases where we are going to use truly quantum sensing mechanisms in the following few slides. We look into superposition, entanglement, or discord states or coherence in the waves that we receive to pick up quantum states. So one more example, and I'm going to move on to the truly quantum part. So in this case, we have a temperature sensor from Texas Instruments chip. So they manufacture a diode, which is actually sensitive to external temperature. So the diode's quiescent current depends on temperature. So if you increase the temperature, the leakage current increases in proportional to the temperature that we apply on the diode. As a result, we actually detect the leakage current as we are forward biasing our diode. So the key idea here is we want to understand how this calibration curve actually behaves as a function of temperature. That's why we look into a systematic study of initial temperature and current readout. We set the temperature again and read out the current, and we essentially observe a higher charge carrier concentration at higher thermal excitation or higher temperatures. And the fact that we have a discretized energy level due to the diode geometry allows us to have or make use of quantum effects in our sensor. But since we are not receiving any quantum state from the thermal excitations, we are actually doing a classical sensing in this sensor. So we need to receive a coherent input or a coherent superposition state or a coherent entangled state to be able to make use of truly quantum sensing. So now that brings us to a definition of quantum sensing from the distinction of classical sensors. So quantum sensing refers to a discretization of energy levels. And in discretization, I'm going to refer to this lower energy state as the state 0, and we are going to have state 1 as our higher energy state. So a two-level system can actually be used for simplifying our perspective, and it can be applied for quite a wide variety of applications in describing quantum sensors, even when they are more complex than this. So quantum sensing uses the changes in the transition energy or the transition frequency between these energy levels. And this frequency can depend on the external stimulus. For instance, if you want to detect external magnetic field, the external magnetic field may cause a shifting of the energy level of 1, and it may cause our omega 0 to become omega naught plus delta omega. And that delta omega will be proportional or monotonically increasing with our external field amplitude. And we also look into this transition rate to pick up this the strength or the stimulus amplitude for our sensor. So typically we want to use a quantum object. So it can be either a material or a device that has quantized energy levels. And we are looking at, in this case, either electronic, magnetic, or vibrational states of superconductor or spin qubits, neutral atoms, trapped ions, or other forms of photonic qubits. In the other case, we want to also use quantum coherence of the external stimulus, if available. And quantum coherence is pretty much the wave-like spatial or temporal superposition of the states. So in this case, the coherence steps up the complexity of the input further. And the last and more advanced version of our inputs are basically some quantum sensors which use entanglement to improve the sensitivity or precision of a measurement. In fact, this is what Özgür Hoca referred to in his final few derivations when he was actually suggesting to use entanglement to circumvent the shot noise limit. Shot noise limit is essentially a fundamental limit that exists in classical sensing. And when we use entanglement, we can actually avoid that limit and achieve much higher precision. In fact, this kind of a sensing scheme was applied to microscopy, and it allowed us to achieve much finer details in our imaging of biological specimens. So the first two types here, the first two definitions can yield both quantum and classical sensing, but the third one is actually a strictly quantum mechanism. And when we refer to the coupling or a transduction parameter, we essentially notice that there's a transition energy that is basically differentiated with respect to our external stimulus, for instance, either magnetic field or electric field, we can say. And then we are essentially looking at either a linear coupling or a quadratic coupling. So these terms actually will have relevance for our sensitivity and variance, and they will help us pick up the actual amplitudes regarding how we can optimize together with the decoherence. So notice that I'm showing you a sensitivity metric here, which is actually giving us an inverse proportion with the transduction parameter, and there's a term, a square root term, that is called the decoherence time of our quantum state. So qubit is a quantum bit, and we are essentially referring to the time over which we can retain our quantum state without distraction from external noise. So in this kind of a system, we want to essentially optimize the coherence time of our implementation together with the way we take this derivative, because this derivative can depend quite significantly on the way we implement our geometry or the material or the energy level difference. In addition to that, the order of transduction parameter is also going to be strongly relevant, and it will show itself in the trapped-ion or photonic or other types of qubits. And each quantum has one or several external parameters that they respond to. For instance, charge systems and spin-based systems will be sensitive to electric fields or magnetic fields respectively. So to give an example for each kind of sensor, we can look into neutral atoms, trapped ions, Rydberg atoms, and solid-state spin ensembles, and solid-state single spins. So these can be quite relevant because they are quite actively studied by many companies in the field. And there are also elementary particle detectors, like fundamental limits that can be detected for gravity or other types of effects. And we can also use single electron transistor for detection of electric field down to the Heisenberg limit, provided we satisfy some conditions. And optomechanical cavities and resonators are basically coupled discretized sensors that basically oscillate with a mechanical characteristic, but they also respond to optical light. So in that case, there's also a transduction between optics and gigahertz frequencies. That's why it can be quite useful, for instance, to bridge these sensors as an intermediate component between quantum components like quantum computers and quantum networks that bring entangled states from the other end of the continent. So optical interferometers are also quite powerful tools that can be used for fine displacement and index sensing. One famous example is the LIGO that you may hear in the in next week's presentations about gravitational detectors. So let me start with the neutral atoms. So these neutral atoms are actually serving as magnetic field or velocity sensors. And we are using alkali ground state spins for our coupled angular momentum and electron nuclear spin characteristics. So we prepare our state by having an external optical pump, and we essentially read out again using an optical probe. So in this kind of a structure, we simply use a moving platform to detect the optical phase shift as a function of the velocity that we use for our cesium vapor cell. And the fact that we use a magnetic shielding allows us to eliminate any kind of splitting of the energy levels due to Earth's magnetic field, which can actually be relevant for fields that we will be reading. In addition, we can actually remove this moving platform and simply have an external magnetic coil, which can be transverse to the applied optical probe, and we can actually measure the magnetic field intensity with extremely fine sensitivities as well. So atomic vapors actually can reach sensitivities as fine as 100 attotesla per square root hertz. So this is actually a sensitivity metric. You can think of it as a unit sensitivity that you would need to multiply by the square root of bandwidth, because if you are operating with a narrow bandwidth signal, you are essentially accumulating extremely small fields, which help you pick up extremely tiny little nanoparticle level intensities. And the coherence times can be pushed to seconds or minutes because of the way the technical chambers have been designed. And theoretical limits were calculated to be as low as 10 attotesla per square root hertz. So this means single particle detection or superparamagnetic limit light detection might be possible using atomic vapors. In addition, there can be cold atomic clouds as well. So using laser cooling, we can reduce the velocity spread of cold atoms, which means we have a number of cold atoms jumping around within a cell, within a box, and then we use our laser, which helps essentially have the atoms have similar velocities, and the reduced spread of velocities enables sensing with longer interrogation times, because it reduces the uncertainty of our readout. And in addition, this is actually relevant for gravimetry, or we can simply measure the height of our lab from the Earth's core. And it can be actually installed on a satellite as well. I mean, these are not too large systems, so this you can actually also measure the rotational rates with, in the gyroscope configurations. So an atomic cloud measures acceleration as well by sensing the spatial phase shift of a laser beam when our atomic cloud is falling freely. And for the case of trapped atoms, we can actually detect the magnetic fields by driving them under Larmor precession. So what does Larmor precession mean? When I'm applying a constant magnetic field, I'm actually causing a precession at the Larmor precession frequency. So that means if I change or detune the frequency, or if I change my magnetic field intensity, I'm essentially causing a shift in my Larmor precession frequency. As a result, we end up with the optical pump or optical probe readout difference. So the spectrum of readout is going to change because of the magnetic field difference. And as a result, we detect the magnetic field intensity or its frequency. But of course, there are many nuances into these measurement steps, and that's what we are going to study in the next few slides. So here I'm showing you some precession peaks that are happening over time. So these peaks are repeating over time as beats, and we pick up the signal from the beats and basically divide by gyrotropic ratio to understand, to obtain how much magnetic field we are applying to our cell. So there are also trapped ions. You may have seen trapped ions for quantum computation purposes. So I'll give you a simple rule of thumb. If there's a bad qubit in quantum computation, it can be a good quantum sensor. So in this case, trapped ions can be used for quantum computation as well, but we want to refer to them as our sensing elements. So the energy levels and the emission spectra of these ions are strongly coupled to the electric field. Since the dipolar transitions of electrons between these ions is actually a strong function of the external electric field. And again, using Raman cooling, we actually detune or basically cause some shift in the energy levels of these ions and achieve megahertz level differences for state transitions. And the next thing that we can see is basically sensitivities for electric fields. So people have started demonstrating sensitivities of electric fields 500 nanovolts per meter. So this is a unit for electric field. And when you divide it by square root of hertz, you are essentially obtaining it as as the electric field sensitivity per bandwidth. So this essentially gives us an idea that our readout scheme is also going to be highly relevant in the way we are going to observe our sensitivity. That is why in quantum sensors, the readout protocol actually becomes a significant subject of research. And once you obtain an optimal point for readout, you actually refine these sensitivities quite significantly. As a result, people have actually invested heavily into their setups or the way they apply their pump and probe signals or magnetic fields or the rates or frequencies of these signals for picking up the highest sensitivity and finest resolution measurement. And when it comes to force measurements, this can also go as low as 1 iota Newton per square root hertz. So we are essentially referring to extremely fine detection limits where you can start observing all the way down to molecular bond forces. So Rydberg atoms can be quite interesting because you may have seen the Nobel Prize given for this research. So these are loosely confined electrons. They have loosely confined electrons in a highly excited orbit that is easily displaced by electric fields. So when we have highly excited orbits, it is going to be practically easier to displace larger spacings between energy levels. And but the caveat is that keeping them steady in those excited states will be shorter. So the atomic energy states are coupled by strong electric dipole transitions, and that's why they observe quite strong splittings of energies, and we call them Stark shifts. And we prepare our quantum states or our initialization of our quantum states by laser excitation, and then we again do an optical readout by sending another probe signal. So these atoms in vacuum have been used as single photon detectors for detecting microwave photons because the energy splittings are small enough to detect weaker microwave photon energies in a cryogenic cavity. So the sensitivities can be as low, as fine as 300 nanovolts per meter per square root hertz, and these can actually help us observe minute electric fields on the chip. So here you may see that, excuse me, here you may see that in the Rydberg case, we use external RF bias to split our energy levels, and the transition upon pumping with optics and then its relaxation will tell us the energy shifts. Basically, when we have one state here, we apply omega RF, which is an external microwave field, for instance, in gigahertz rate, and then we split the energy levels, and then we apply optical pulse, and then we excite our electrons over the allowed dipolar transitions. And then due to the allowed dipolar transitions, we only have several transitions that can actually appear in our probe's emission spectra. So what I do next is apply a probe's pulse from the laser, and then see how the emission can be observed in real time, or you can simply pick it up after the transition occurs as an emission from the cell. So this is one of the ways you can read out. When it comes to solid state ensembles, we are actually referring to an entire group of atoms that act together for our measurements. So we are essentially looking at multiple atoms, and their nuclear resonance, or their nuclei, actually have spins, and they have precessions that are coordinated. So this concerted precession can be triggered by our state preparation. So what we do is we actually apply an external magnetic field, and then we essentially apply an external bias that we want to read. So essentially what we are observing is this excitation through the AC excitation step is the field that we want to measure. So we want to actually measure B1 magnitude, and essentially this bias actually causes a phase shift or a frequency shift in the precession of the atomic ensemble. And then we let it relax, and the relaxation time and the voltage signal that we pick up helps us recover the magnitude of the external magnetic field that we apply. So this way, sensitivity is as fine as 10 picotesla per square root have been achieved. So these are actually not as fine as the previous ones that I showed, but you can actually improve them quite significantly by embedding your readout scheme in interferometers like Sagnac interferometry. So this can be quite useful. And I want to talk about also diamond NV centers, which are nitrogen atoms and carbon vacancies within diamond lattice. So when you have this diamond crystal, you can have pairs of nitrogen and vacancy centers, and this complex can actually come together in a large number of pairs, and it allows you to pick up a large strong fluorescence signal that is triggered because of the red emission as a result of the pulses that we apply. I'm going to come back to this figure or the diamond centers later in more detail, but the idea is that these are the given energy levels, these are the triplet levels, and the singlet levels are actually the dark transitions, which means when I apply a green laser, I excite my electrons first. So the ways our electrons can relax are basically through either the singlet states, which are dark, we don't get their optical emission, or through the red emissions. So the red emission can fall back to either ms equals 0 or mx equals plus or minus 1 states. Remember that these quantum numbers are going to actually have different footprints in the spectra if we apply a small enough microwave field externally, so that we can have slight energy differences for our distinction of which transition is occurring. So since I want to understand which state I'm actually triggering or controlling, I want to understand whether I'm transitioning from 0 till +1 or 0 till -1 or vice versa. So this is actually quite relevant for storing information because that kind of readout is going to be also time dependent and external field dependent. And the fluorescence signal is actually going to be my main tool for detecting these emissions. So we are essentially reading out the red fluorescence intensity. So when it comes to single spin sensors, we are essentially giving up on using an ensemble of diamond NV centers, but instead we focus on only one pair of nitrogen and vacancy centers. So we are essentially doing what we call a Ramsey sequence, which means we are essentially applying, again, laser and microwave pulses, but this time we are going to start introducing these kinds of sequence plots. So these are essentially state preparation, relaxation, and readout steps. So these steps are actually going to be relevant for the way they decay and what frequencies we get and how fast they decay. So these are the important readings, especially from the photoluminescence as a function of time for our sensor chips. So what we do in this kind of a system is we first excite, with 532 nanometers, which is the green laser as I showed you previously. And then we set our state to up orientation, as you will. And then we apply a microwave pi/2 pulse, which is a short enough pulse that will lead to a superposition of our initial state to a superposition state. So in the superposition state, we are essentially observing our spins to basically have some phase shift, and it causes our spin up and down states to have some mixture. And then what we do next is we are letting the system relax by waiting a duration of tau. And then in this bell state configuration, we are going to apply another microwave pulse finally, which is again pi/2 duration. And we finally apply another optical pulse for detecting the fluorescence of the remaining state. During this relaxation period, we actually apply the external magnetic field that we want to read. As a result, we get these Ramsey sequences as we are doing the readout. So what we do to get these plots is basically we vary the tau and repeat this whole experiment for different tau values. And after that, we read the photoluminescence at the end of our readout step. And for each point, we have a separate reading. We have, for one tau, we have about 0.15 PL contrast. And then as we increase tau, we observe these oscillations because of the external fields damping on the precision. So we can also now define what makes our sensing purely quantum, or how it is actually relevant for our applications. So we can actually observe higher sensitivities beyond state-of-the-art classical magnetometers, accelerometers, or gyroscopes, or photodetectors, or other commercial sensors. For instance, the state-of-the-art magnetometers or accelerometers or gyroscopes can be purchased from different companies in packaged electronic chips. but using atomic sensors, you can actually get extremely finer magnetic field resolution. And if you use also entangled states, as I showed you in the earlier examples, we might actually beat the shot noise limit and go as low as Heisenberg's limit, which is what Özgür Hoca derived in the previous lecture. So this is actually possible, and we are actually going to need to prepare our states properly. One more example is actually using these sensors for single molecule or single virus detection. In this example, I'm showing you a fluorescent nanodiamond, which is conjugated to basically double-strand DNA and the streptavidin layer to bind onto the surface, and the virus essentially attaches on the DNA. And what happens is our ring here, which receives a pulse, electric pulse, basically applies a field, inductive field onto this system. So in this case, we are observing a HIV virus, and this HIV virus binds onto the DNA strand, which is specific to the proteins or the spike proteins of the external structure. As a result, what we do is we detect the fluorescent peak shift and intensity shift by varying the concentrations that are applied on our chip. And once we do that, we can actually observe the pump. So we excite with green, and then we read around red or near infrared, and then we turn on microwave on, and we turn it off, so we observe a difference, and this difference can help us pick up our contrast for the virus as well. And the fluorescence peak difference can also be amplified because of the virus binding into the chip. So what they did here is essentially varying the fluorescent nanodiamond concentration, and then they looked into the signal to blank ratio while applying the field, and then we can actually detect extremely low concentrations of the double-strand DNA, and by applying a microwave, we can actually observe the contrast with the virus as well. So now let's start picking up, excuse me. Now let's start picking up on the quantum sensing part through the Hamiltonians. So we can basically decompose our Hamiltonians into several terms. One is the internal Hamiltonian that depends on the implementation. So superconducting systems or diamond NV systems or others can have their own internal Hamiltonians, but the core idea is that we want to have our external signal that is also modulated or controlled with our control signal. So what we do here is we apply our external field or external voltage, which also changes H0 and HV. HV is essentially the signal that we want to read, and these kinds of the oscillations that we have in the H control or in the DC form can help reconstruct the amplitude or the phase of our external signal. So this is the starting point for the classical sensing, and the way we control H0 is through the implementation or the device geometry, and the way we control H control is through our external bias or parametric sweeps. This way, we observe how we can pick up or reconstruct HV in our solutions. So I'm going to let I'm going to wrap up only through the quantum sensing protocol here, and I'm going to I can have a more detailed presentation for these parts later, but the whole idea is that we want to first initialize our quantum sensor into a zero state, and we use a pi/2 pulse, as you may remember in the block sphere. We essentially had the initial superposition state, and then what we did is we let our state evolve, and it picked up a relative phase over this time step. So, but notice that this omega actually is not just random omega. It is originating because of the precession due to the external magnetic field. So this has some relevance due to the external magnetic field. And this phase factor is going to be something that we are going to actually pick up at the end of our measurements. So what we do next is when we are applying our field using a second pi/2 microwave pulse, we essentially, convert back to the measurable state. So we are essentially doing the following. We essentially apply another pi/2 pulse and essentially start with plus state, but now have another plus state of this one. And that's why when you open it up and group 0 states and 1 state, you essentially get these coefficients for 0 and 1. And finally, when we do the state readout from a probe spectrum readout, the transition probability is going to be essentially the 1 minus inner product of 0 alpha state. And we are essentially picking up this sine square omega naught t/2. So this recording p as a function of time in an oscillatory output that we had here is actually going to be giving us the rate at which our magnetic field causes the decay. And through our controlled bias of magnetic field, we can actually deduce a calibration curve for our sensor and finally pick up as deduce a sensitivity and noise limit for our detectable frequencies of bias and amplitudes of bias. So I'm going to give you some more examples and conclude. Diamond NV sensors are actually quite commonly used because they actually help us retain information over longer periods of time due to the wide band gap of diamonds. This reduces the phonon density of states and causes longer decoherence times. As a result, you can retain the information or the state here for longer periods. So that means if you have this block sphere, the transition from one state to the other or the relaxation times can be longer than other types of systems. And in this case, again, we have the similar energy transitions. And what people did is they applied external magnetic field and observed the changes in the plus and minus 1 states of the triplet ground states. And through the microwave spectroscopy, meaning transmission of our input microwave pulses and reading of the transmitted microwave frequencies, we can actually deduce which peak, which state actually absorbed the resonance. So we actually take a slice through the spectrum and see that these red and blue points actually cause a dip in our measured spectrum. And people have also shown how applied optical power can change our bandwidth by more than an order of magnitude. And there are also ways to actually see this effect in other ways than microwave transmission, and that's through photoluminescence. And photoluminescence actually helps you pick up electron spin resonances within the diamond NV pair. And there are other ways, for instance, if you confine it into a cavity, you can reduce the sensitivity even further. And by applying external temperature, you can actually cause shifting in the frequencies even further. And applying external voltage can also shift these optically detected magnetic resonance peaks even further. So these dips are called ODMR peaks, which are abbreviated as optical ODMR, optically detected magnetic resonances. And let me wrap up. We know sensing can be actually done quite easily, and many classical sensing techniques actually originate from quantum effects. But not all of these sensors are actually quantum sensors, because we don't coherently detect the phase or the amplitude or the superposition of the wave function of our external stimuli or the wave-like particles. And the next thing that we check for is the detection of the wave function coherently. So to do this, we need to really actually prepare our state in our system. And once we can achieve this state preparation, and once we do this state readout, we can actually beat the shot noise limit and reach extremely high sensitivities down to the Heisenberg limit, or exceed the Rayleigh limit, or go beyond classical trade-offs. So you have seen the examples in which people have explored these capabilities. And there are, of course, lots of opportunities, for research for your own future graduate studies or for your other curiosity. For instance, in sensors, the noise inefficiency and bandwidth limitations or sensitivity and dynamic range trade-offs exist. And these trade-offs are actually also coming with the readout electronics. And the sensing protocols that I mentioned, for instance, the Ramsey protocol is only one of them. And achieving the implementation through the correct materials fabrication or the device fabrication is also another challenge. And finally, people have proposed quantum error correction, which is essentially taking a reference qubit that is not affected by external magnetic field for essentially better subtraction of the signal. In this case, we can have even better sensitivity, and we can use multi-qubit sensors for even finer sensitivities. And this actually brings me to the last part, which is actually the cutting-edge research on, for instance, quantum phase estimation, variation of quantum circuits, which can be used for exploring the optimization of these sensing protocols further. So let me end with giving a quick little homework. So I would like you to look up your favorite sensor type, quantum sensor type, from the papers published in the journals that I showed, and pick one, and explain how this the sensor of your choice works, and then explain what makes this sensor a quantum sensor, and how does this sensor compare with classical sensors or other quantum sensors. So with that, let me share the link to you for my presentation slides. And I can also do another follow-up quantum sensing lecture to give you more details on the concepts that I have actually glossed over. For instance, noise spectroscopy, ensemble sensing, sensing assisted by auxiliary qubits. If you're interested, I'm going to share with you this link so you can sign up and we can have another discussion at a later time. Thank you very much.
Thank you, Cengiz. We are quite long over time, so I'll just take one question, then you can discuss later on. So Ekrem Tagil has asked, I'm just directly reading from the chat area. Is it experimentally possible to isolate single MV center from an ensemble of MVs in diamond structure and execute measurements via choosing MV center to characterize T2 relaxometry of that MV center or to measure the unknown magnetic field?
It's actually possible. I have glossed over in my in one of the presentations, but in the slides. So let me show you one case where it is actually feasible to pick up individual NV centers. For instance, when you see this one little cone here, this is actually engineered to pick up individual NV center. People have been using confocal fluorescent or confocal photoluminescent microscopy with a piezoelectric stage that controls the position of our readout to pick up individual isolated NV centers from chip. And then what we do is we excite the whole chip, but only pick up signals or fluorescence from that individual NV center. So this allows us to actually read individual NV centers T2 signals.
Thank you. So we need to stop here. Now we have a lunch break. We will meet again at 1 o'clock with the lecture of the Professor Ceyhun Bulutay on quantum information and quantum optics. If you have further questions to Professor Onbaşlı, just send him an email. Then he already provided the link. There's a message, Hocam, we have not access to the link, but Professor Onbaşlı checked that drive link and communicate directly with him. So see you again at 1 o'clock with the same link. Okay. We have a half an hour lunch break.